The universe is far stranger than we ever thought. For centuries, we believed we had its basic rules figured out, but we were wrong. Across the cosmos, structures of impossible scale and bewildering behavior are being discovered, each one a direct challenge to our fundamental laws of physics. This journey will explore 25 of these cosmic anomalies, from colossal walls that should not exist to voids of staggering emptiness. You will discover why the most established scientific models are failing to explain reality. What mysterious force could be pulling entire galaxy clusters in a single direction? And could our entire local universe actually be sitting inside a giant cosmic void? By the end, you will see the cosmos not as a settled map, but as a frontier teeming with profound mysteries. What single cosmic discovery do you think could most radically reshape our understanding of everything? Stretching across an almost unimaginable 10 billion light-years, the Hercules-Corona Borealis Great Wall is not merely large. It is the single largest known structure in the entire observable universe. To grasp its scale, consider that a single light-year is the distance light travels in 1 year, moving at a speed that could circle our planet 7 times in a single second. Now multiply that by 10 billion. This cosmic wall is a filament, a vast web-like structure made of thousands upon thousands of galaxies, all bound together by gravity. Its discovery sent shockwaves through the world of cosmology because it directly confronts one of our most fundamental assumptions about the cosmos, the cosmological principle. This principle states that on a very large scale, the universe should look roughly the same everywhere, no matter where you are observing from. It should be smooth and homogeneous, like a well-mixed batter. But the Hercules-Corona Borealis Great Wall is a glaring lump in that batter. It is a structure of such immense proportions that it should not exist according to our standard models of the universe. The problem runs even deeper than its mere existence. This colossal wall was found at a tremendous distance, meaning we are seeing it as it was when the universe was still relatively young. The models struggle to explain how gravity could have pulled together so much matter into one coherent structure in the relatively short time since the Big Bang. It is like finding a fully grown ancient forest in a landscape that, by all accounts, should only be sprouting seedlings. This has sparked intense debate among scientists. Some propose that our understanding of the early universe is incomplete, perhaps missing a key ingredient. Others scrutinize the data itself, wondering if we are seeing a trick of perspective, a chance alignment of smaller clusters that only appears as a single titanic wall. Yet the evidence remains stubbornly present, a monumental challenge etched across the sky. For a time, the Hercules-Corona Borealis Great Wall had a rival for the title of largest cosmic structure, a discovery that first truly shattered our expectations of the cosmos. The Sloan Great Wall, a sprawling filament of galaxies stretching an astounding 1.37 billion light-years, was mapped in the early 2000s by the Sloan Digital Sky Survey. This ambitious project used a dedicated telescope to meticulously catalog millions of celestial objects, creating an unprecedented three-dimensional map of our universe. When scientists analyzed this map, the Sloan Great Wall emerged, a staggering river of galaxies so vast it seemed to defy the very principles of a uniform universe. Imagine a formation so long that if you could travel at the speed of light, it would take you over 1 billion years to go from one end to the other. This was not just a cluster, it was a backbone of the cosmic web, a structure of a scale that theorists struggled to account for. its discovery forced a profound question. How could the gentle tug of gravity, acting over the age of the universe, have assembled something so immense and coherent? Our best models of cosmic evolution simulate how the universe grew from a nearly smooth state after the Big Bang into the web we see today, but they consistently predicted a limit to how large these structures should become. The Sloan Great Wall, and later the Hercules-Corona Borealis Wall, stepped right over that theoretical line. They are not just astronomical curiosities. They are evidence that our simulations might be missing a crucial piece of physics, or that we are fundamentally misjudging the raw power of gravity on the largest scales. The existence of these titan walls suggests the cosmos might be lumpier, more textured, and far more unpredictable than we ever believed. Yet for every colossal wall of galaxies, the cosmos presents its opposite, a staggering emptiness that is just as confounding. The Boots void is one of the largest known voids in the universe, a spherical region of space so profoundly empty it has earned the nickname the Great Nothing. Stretching approximately 330 million light-years across, this void is not just a sparsely populated area. It is a cavern of near-total vacancy. If our Milky Way galaxy sat at the center of the Boots void, we would not have known other galaxies existed until the 1960s. The sheer scale of this nothingness is what defies belief. According to our understanding of how matter should be distributed, a region this vast should be home to thousands of galaxies. Instead, astronomers have found only a handful, perhaps 60, scattered like lost stars in an immense dark ocean. This presents a deep cosmic puzzle. How can such a vast volume of space contain almost nothing? One leading theory suggests that the Boots void is not a single, primordial emptiness, but the result of smaller voids merging together over billions of years. Think of soap bubbles in a sink, slowly coalescing into one giant bubble. The gravitational tug of the dense walls of galaxies surrounding the void could have slowly drained it of matter, pulling galaxies away and leaving behind an ever-expanding desert. But this explanation is still not entirely satisfactory. The scale remains almost too large for our models to comfortably account for. The void challenges the cosmological principle in a different way than the Great Walls do. Instead of too much structure, it shows far too little. It forces us to ask if the distribution of matter in the universe is not just lumpy, but also filled with gaps of a magnitude we are only beginning to comprehend. What other vast emptiness might lie just beyond our current view, silently reshaping our map of the cosmos? From the immense emptiness of the Boots void, we turn to a structure of breathtaking and delicate beauty. Hoags-object is a galaxy that defies all common classifications. It is not a spiral like our Milky Way, nor a simple blob like an elliptical galaxy. Instead, it presents itself as a nearly perfect cosmic ring, a circle of brilliant blue stars surrounding a separate golden core. This celestial bullseye, floating in the darkness of space, is so symmetrical it appears almost artificial. The core is a dense sphere of ancient yellow stars, while the outer ring is a vibrant, young nursery of hot, blue stars, actively giving birth to new suns. What makes this object so profoundly puzzling is the vast, completely dark gap that cleanly separates the two components. There is no bridge of stars, no visible spiral arms connecting the core to the ring. They exist as two distinct entities, one neatly framed inside the other. How could such a perfectly isolated structure form? The most intuitive theory points to a violent past, suggesting a smaller galaxy once shot straight through the heart of a larger one. This cosmic collision, much like a stone thrown into a pond, could have sent ripples of density through the galaxy, triggering a wave of star formation in a perfect circle while leaving the central core undisturbed. However, there is no evidence of a culprit galaxy, no remnant or debris that such a collision would inevitably leave behind. Another, more subtle theory proposes an extreme case of resonance. In this scenario, a central bar of stars, which has since dissolved, could have created a gravitational resonance zone, a specific ring-shaped region where gas was compressed and forced to collapse into new stars. Over time, this would have created the brilliant blue ring we see today, while the bar itself faded away. Yet, the pristine perfection of Hoags-object remains exceptionally rare, a cosmic fluke that our models struggle to replicate. Its serene appearance masks a turbulent and mysterious history, a single, perfect question mark written in starlight. Yet even the perfect symmetry of Hoags-object is not the universe's most direct challenge to our fundamental rules. Hanging in the distant cosmos is a structure known as the Giant Arc, a vast, crescent-shaped formation of galaxies that spans an almost incomprehensible 3.3 billion light-years. This is not a solid wall, but a coherent curve of galactic clusters, gaseous filaments, and dark matter, tracing a graceful arc across the sky. Its discovery was a masterclass in cosmic detective work. Astronomers did not simply take a picture of this immense structure. Instead, they painstakingly analyzed the light from incredibly bright, distant objects called quasars. As this quasar light travels for billions of years to reach us, it passes through clouds of hydrogen gas in the cosmic web. These clouds imprint a specific signature, known as the Lyman alpha absorption line, onto the light. By mapping where this signature appeared and disappeared across thousands of quasars, scientists could essentially trace the outlines of the invisible gas clouds that make up the universe's large-scale structure. When they pieced this map together, the giant arc emerged, a pattern so vast it should not be possible. The cosmological principle, the foundational idea that the universe should be roughly the same in all directions when viewed on a large enough scale, sets a theoretical size limit for structures. That limit is about 1.2 billion light-years. The giant arc is nearly 3 times that size. Its sheer scale suggests that the universe is not as smooth and homogeneous as we have long assumed. Instead, it appears to be textured with imbalances and patterns on a scale that our standard model of cosmology simply cannot explain. This crescent of galaxies is more than a curiosity. It is a fundamental question mark, forcing astronomers to wonder if our entire understanding of the universe's structure needs to be rewritten. But what if the universe itself is moving? Astronomers have detected a phenomenon so strange, it seems to defy the very expansion of space, a mysterious current they call the dark flow. Across the cosmos, entire clusters of galaxies appear to be streaming in a single, specific direction, as if pulled by a cosmic tide. This is not the random drift of individual galaxies. This is a coordinated motion on an unimaginable scale, with thousands of galaxy clusters all flowing together at astonishing speeds. The evidence for this eerie movement comes from a surprising source: the afterglow of the Big Bang itself, the cosmic microwave background. This ancient light fills the entire universe, and it provides a fixed reference frame, a backdrop against which all other motion can be measured. By studying how the hot gas within these distant galaxy clusters subtly shifts this background radiation, scientists can detect their velocity. The results were shocking. These clusters are not just moving with the general expansion of the universe. They have an extra, unexpected velocity, and they are all heading the same way. This collective motion is the dark flow, and its implications are profound. What immense gravitational force could possibly be tugging on thousands of galaxy clusters? The most startling possibility is that the source of this pull lies beyond the edge of everything we can see, beyond our observable universe. This suggests that the colossal structure of the cosmos does not end at our visual horizon. There could be regions of space, perhaps with vastly different distributions of mass, exerting a gravitational influence on us from the outside. Some theorists have even proposed a connection to the multiverse, suggesting the flow is evidence of a neighboring universe, a separate bubble of reality, gravitationally tugging on our own. Others wonder if it is an echo from a time before the Big Bang, a relic of some primordial imbalance. Of course, the dark flow is hotly debated. Many scientists question the data, suggesting it could be a statistical fluke or a misinterpretation of the measurements. Yet if it is real, it points to a cosmos far grander and more interconnected than we ever dreamed, where the boundaries of our reality are not walls, but mere windows into a deeper, darker ocean. While the dark flow hints at unseen forces beyond our cosmic horizon, another anomaly imprinted on the oldest light in the universe presents a different kind of mystery. A strange and profound chill lingers in the afterglow of the Big Bang. This is the cosmic microwave background cold spot, a region of space that is significantly colder than its surroundings. Discovered first by the Wilkinson Microwave Anisotropy Probe, and later confirmed in stunning detail by the Planck satellite, this cold spot is not a small imperfection. It spans a colossal billion light years across, a vast patch of sky that is unusually and mysteriously cold. The cosmic microwave background is the remnant heat from the birth of the universe, a nearly uniform blanket of radiation that fills all of space. Tiny fluctuations in its temperature are normal, the seeds from which all future galaxies would grow. But the cold spot is not tiny. Its temperature is so exceptionally low that it stands out as a significant statistical outlier, a deep freeze that our standard models of cosmology struggle to account for. What could possibly cause such a vast and intense cold region? One leading and mind-bending theory suggests it is a cosmic texture defect. Imagine the fabric of spacetime itself underwent a phase transition as the infant universe cooled, much like water freezing into ice. Sometimes during this process, the fabric could have become tangled, creating a defect, a knot in the very structure of reality. If such a texture existed and then unraveled, it would have released a tremendous amount of energy, creating a gravitational well that would redshift light passing through it, making that region of the cosmic microwave background appear colder to our instruments. Another, even more radical, explanation posits that the cold spot is a bruise, a remnant of a collision with another universe. In the multiverse theory, our universe is just one bubble in a vast cosmic foam, constantly inflating and sometimes bumping into other bubbles. If our universe had such a collision in its distant past, the energy drained away into the other universe could have left behind a cold, empty imprint on our sky, a cosmic scar from a battle between realities. Of course, more conventional explanations are also on the table, such as the possibility of a truly immense supervoid, an emptiness so vast that it drains the energy from light passing through it. Yet, searches for a void large enough to explain the cold spot have come up empty. This leaves us with a profound puzzle written in the universe's first light, a chill that may be a flaw in spacetime's fabric or a window into the multiverse itself. These cosmic scars and flows are not the only large-scale mysteries. Drifting in the distant, early universe are objects of such immense and ethereal beauty they seem almost like celestial ghosts. They are known as Lyman alpha blobs, and they are among the largest single structures ever identified. A single blob is a colossal cloud of primordial hydrogen gas, spanning hundreds of thousands of light years across, sometimes even millions. To put that in perspective, one of these blobs could easily engulf our entire local group of galaxies, with room to spare. They are not solid objects, but vast, diffuse nebulae, glowing with a specific, haunting hue of ultraviolet light. This is the Lyman alpha line, the signature of hydrogen gas as it releases energy. And that is the central puzzle. What could possibly make these gargantuan clouds of simple gas shine so brightly across such immense volumes of space? The energy required is staggering, like lighting up an entire ocean from within. Astronomers have proposed several theories, each one a dramatic cosmic process. The first is a frenzy of creation. Perhaps these blobs are the sites of the most intense star formation in the universe, where entire galaxies are being built at a ferocious rate. Millions of newborn stars, each one far more massive and brilliant than our Sun, would flood the surrounding gas with ultraviolet radiation, causing the entire cloud to fluoresce, much like a neon sign. Another theory points to the most violent objects known to science, active galactic nuclei. At the heart of these blobs, a supermassive black hole could be feasting on surrounding matter, releasing such titanic amounts of energy that it lights up the entire gaseous envelope for vast distances. The energy output from a single quasar can outshine an entire galaxy, and that power could easily illuminate a blob. Yet a third, more subtle idea suggests the glow comes from the clouds themselves as they cool. In this scenario, the blobs are massive reservoirs of gas, steadily collapsing under their own immense gravity. As the gas falls inward, it heats up, and then it must radiate away that heat to continue collapsing. This cooling radiation itself could be the source of the Lyman alpha glow, a cosmic sigh as the cloud settles into a new structure. The truth is, these mechanisms might all be at play in different blobs, or even within the same one. They represent a critical yet poorly understood phase in the assembly of the largest structures in the cosmos. These glowing behemoths are not just static clouds. They are cosmic wombs, potentially giving birth to galaxy clusters, or the graves of ancient galactic mergers, their gentle light a testament to the raw, energetic forces that shaped the early universe. Our own galactic home holds a secret of titanic proportions. Extending for 25,000 light years above and below the center of the Milky Way are two colossal spheres of energetic radiation, known as the Fermi bubbles. These are not bubbles of gas in the traditional sense, but immense structures filled with ultra-hot magnetized plasma, glowing fiercely in the highest energy form of light, gamma rays. They remained completely hidden from view until the Fermi Gamma Ray Space Telescope, designed to scan the sky for these powerful emissions, mapped them in stunning detail. The bubbles form a perfect symmetrical hourglass shape, with our galaxy's central black hole, Sagittarius A star, sitting squarely at its narrow waist. This perfect alignment is a crucial clue to their violent origin. The central question is what kind of cataclysm could have forged these structures. One leading theory points directly to the dormant giant at our galaxy's heart. Astronomers suggest that several million years ago, Sagittarius A star might have experienced a period of intense activity, feeding on a vast amount of surrounding gas and dust. This feeding frenzy would have unleashed a pair of colossal jets, erupting from the black hole's poles at nearly the speed of light. These jets would have blown enormous cavities in the gaseous halos surrounding the Milky Way, inflating the bubbles we see today. An alternative theory proposes a different, yet equally dramatic, source. The galactic center is also a region of intense star formation. A sudden, explosive burst of star birth could have created a wave of supernova, with each dying star blasting its outer layers into space. The combined force of thousands of these stellar explosions happening in a relatively short cosmic time span could have collectively blown these giant bubbles, pumping them full of energetic particles. The debate continues because both scenarios leave different imprints on the bubble's structure and the energy of the particles inside. The black hole jet would create a sharper, more defined edge, while the starburst model might produce a more turbulent and mixed interior. Unraveling this mystery is like galactic archaeology, digging into a violent event from our Milky Way's past that, for a brief moment, turned our quiet neighborhood into a cosmic furnace, its echoes still visible today as a ghostly, glowing silhouette against the deeper universe. This very galaxy we call home might be floating inside a cosmic anomaly. The KBC Void, named for astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, proposes a startling idea. Our entire local universe, including the Milky Way and our neighboring galaxies, resides within a vast bubble of relative emptiness. This is not a complete vacuum like the Boots Void, but a significant underdensity, a region where the concentration of galaxies and matter is far lower than the cosmic average. We are not in a special place, but rather in a cosmic backwater, a quiet suburb in the metropolis of the universe. This seemingly humble observation might hold the key to one of the most pressing problems in modern cosmology, the Hubble tension. This tension is the growing discrepancy between two methods of measuring how fast the universe is expanding. One method uses the cosmic microwave background, the ancient light from the Big Bang, to predict the expansion rate. The other measures it directly by observing stars and supernova in our nearby universe. These two methods, one looking at the ancient cosmos and one at the modern one, are giving us different answers. They refuse to agree. If we are truly sitting inside a giant void, it could resolve this conflict. The reasoning is gravitational. A region with less matter has a weaker gravitational pull. In such an underdensity, the fabric of space would expand slightly faster than in the denser universe outside. Our local measurements of supernova would be capturing this boosted local expansion rate, while the cosmic microwave background reflects the true global average. We would be mistaking our local environment for the entire cosmos. The implications are profound. It would mean our most precise measurements of the universe's expansion are subtly biased. Our cosmic neighborhood is not a standard sample. It is an outlier, a quiet pocket that misrepresents the louder, denser universe beyond. If true, it forces a deep humility upon us. The very spot from which we observe everything might be skewing our perception of reality itself. This mysterious pull we feel is not just a current, but a destination. For decades, astronomers have known our Milky Way is not drifting aimlessly through the cosmos. Along with our entire local group of galaxies and thousands of others, we are racing through space at a breathtaking speed of over 2 million kilometers per hour, all towards a specific, hidden point in the sky known as the Great Attractor. The name itself evokes a sense of a cosmic siren, a gravitational monster lurking in the void, pulling everything towards it. The reality, however, is far more complex and difficult to see. Our view to this enigmatic region is completely blocked. It lies in the direction of the constellation Norma, positioned directly behind the crowded, dusty central plane of our own Milky Way galaxy. This area is so obscured by interstellar gas and countless stars that astronomers call it the zone of avoidance. It is the ultimate cosmic blind spot, hiding what may be one of the most significant gravitational landmarks in our intergalactic neighborhood. Peering through this galactic fog requires special tools, telescopes that see in wavelengths other than visible light, like infrared and radio waves. These instruments have begun to lift the veil, and they reveal that the Great Attractor is likely not a single, unimaginably dense object. Instead, it appears to be the core of a colossal supercluster of galaxies, with a massive galaxy cluster called the Norma Cluster at its heart. This entire region is an immense concentration of mass, a gravitational anchor so powerful that it dominates the motion of an entire sector of the universe. The sheer weight of thousands of galaxies, along with their associated dark matter, creates a deep well in the fabric of spacetime, and we are simply sliding down its slope. Yet even this massive supercluster might not be the full story. Our motion continues beyond it, suggesting an even larger, more distant source of gravity is at work. A reminder that our journey through the cosmos is guided by forces we are only beginning to map. But the Great Attractor is not the only heavyweight in the cosmos. Far beyond our local neighborhood, at a staggering distance of over 7 billion light-years away, lies a true colossus. It is known as El Gordo, Spanish for the Fat One, and its official designation is a sterile string of letters and numbers, a CT-CLJ0102-4915. This galaxy cluster is one of the most massive and the most violent ever observed in the distant universe. El Gordo is not a serene collection of galaxies. It is a cosmic train wreck in progress, a site of immense and ongoing collision. Within its heart, two separate galaxy clusters are smashing into one another at millions of kilometers per hour. This titanic impact has created a distinct substructure that astronomers call a bullet cluster, a name that perfectly captures its explosive nature. As the two clusters collided, their vast clouds of hot gas, which make up most of their normal matter, slammed together. This intergalactic plasma, heated to extreme temperatures, slowed down and piled up in the center, creating a glowing, monstrous core. But the galaxies themselves, along with something far more mysterious, behaved very differently. The thousands of individual galaxies within the clusters, separated by vast, empty spaces, simply passed through one another like swarms of ghosts, largely unaffected by the collision. Even more telling, maps of the cluster's total mass, created by measuring how its gravity bends the light from more distant galaxies, reveal that the bulk of the mass is not where the glowing gas is. The true weight of the cluster lies in two distinct clumps, aligned with the galaxies that have clearly sailed right through the cosmic wreckage. This is considered one of the strongest pieces of evidence for the existence of dark matter. The explanation is elegant. The colliding gas clouds interact strongly because they are made of normal particles. But dark matter, which does not interact with light or normal matter, felt only gravity. It and the galaxies, which are also dominated by gravity, simply followed their trajectories, completely unaware of the violent gaseous turmoil they left behind. The bullet cluster shows us that most of the universe's matter is truly dark and separate from the stuff we can see. Yet El Gordo presents another, deeper puzzle. Its sheer mass and mature state, complete with this complex collision, are seen at a time when the universe was only about half its current age. Our best models of cosmic structure formation have a difficult time explaining how gravity could have assembled something so immense so quickly after the Big Bang. It is like finding a fully formed, warring empire in an era that should only contain scattered, primitive tribes. El Gordo is not just a giant. It is a precocious giant, forcing us to question the timeline of how the universe built its largest inhabitants. Drifting in the darkness of the Sculptor constellation, a perfect circle of galaxies challenges our very notion of cosmic architecture. Known simply as the Giant Ring, this structure spans 5 billion light-years across, a near-flawless circle of stellar cities so vast it defies easy explanation. We are accustomed to a universe of filaments and walls, a tangled cosmic web, but a perfect ring on this scale is something entirely different, a geometric oddity that seems almost too perfect to be natural. Its discovery was a shock, a pattern so coherent it immediately stood out as a statistical anomaly in sky surveys. How could gravity, which typically builds sprawling, uneven structures, arrange matter into such a symmetrical form? One compelling theory reaches back to the universe's very first moments. In the primordial plasma that filled the cosmos before the first stars, sound waves propagated outward from tiny density fluctuations. These waves, known as baryon acoustic oscillations, created ripples in the hot soup of matter, setting a preferred scale for how matter would later clump together. The giant ring could be a frozen relic of one of these ancient sound waves, a single vast ripple imprinted on the cosmos and preserved for billions of years, now visible as a ring of galaxies. It would be a cosmic fossil of unbelievable size, a direct snapshot of the universe's infant cries. Yet another, more exotic possibility exists. The ring could be the result of a gravitational ripple, not in matter, but in the fabric of spacetime itself. A long-ago collision with a primordial black hole or a massive texture defect in spacetime could have sent a shockwave propagating outward, a circular tsunami that compressed matter in its wake and triggered the formation of galaxies along its leading edge. This would make the ring a bruise on the cosmos, a scar from a traumatic event in the deep past. Both theories push the boundaries of our understanding, forcing us to consider whether the largest structures we see are not just products of gravity, but also echoes of the universe's most violent and fundamental processes. Is this beautiful ring a remnant of the first sound, or the ghost of a forgotten impact? Its perfect geometry offers no easy answers, only a deeper mystery written in the arrangement of galaxies. This invisible architecture may be the most profound challenge of all. We have been exploring cosmic giants built from stars and gas, but these are merely the glittering ornaments on a much deeper, darker framework. The true backbone of the universe is woven from dark matter, a substance that neither emits nor reflects light. Its presence is felt only through its immense gravitational pull, a ghostly hand guiding the motion of everything we can see. Each galaxy, including our own Milky Way, is embedded within a vast, spherical halo of this mysterious material. These dark matter halos are not small. They extend far beyond the visible edges of their galaxies, forming immense, invisible spheres that can span hundreds of thousands of light years. It is within these halos that the first galaxies were born, their gravity providing the initial seeds for normal matter to collapse and form stars. For decades, our standard model of cosmology, known as the lambda cold dark matter model, has used supercomputer simulations to predict how these halos should behave. The simulations produce a universe that looks remarkably like our own, with a cosmic web of filaments and clusters. But when we compare the simulated dark matter halos to the real ones we infer from observing galaxies, a troubling discrepancy emerges. It centers on the very heart of these halos, their density profile. The simulations consistently predict that dark matter should be densely packed at the very center of a halo, forming a sharp peak or cusp. The density should rise steeply as you approach the galactic core. Yet observations of many dwarf galaxies, which are dominated by their dark matter halos, tell a different story. Instead of a sharp cusp, the dark matter in these galaxies appears to be distributed in a constant density core, like a soft, fluffy center. The density remains relatively flat all the way into the middle. This is the cusp core problem, and it is a major headache for cosmologists. How could our simulations be so right on the large-scale structure of the universe, yet so potentially wrong on the scale of individual galaxies? Something must be happening within these halos that the simple simulations are missing. Perhaps the answer lies with the normal matter we can see. The violent and complex physics of stars, supernova, and gas may be stirring up the dark matter. Intense bursts of star formation could create powerful galactic winds, pushing normal gas around and, through gravity, effectively sloshing the dark matter in the center, smoothing out the predicted cusp into an observed core. Another, more radical possibility is that dark matter is not completely cold and collisionless as we have assumed. What if dark matter particles can interact with each other through some unknown force, a faint whisper of interaction that allows them to scatter and redistribute their energy, naturally preventing a dense cusp from forming? This single puzzle, hidden within the invisible hearts of galaxies, forces us to question the fundamental nature of the universe's primary ingredient. Is dark matter simpler than the complex normal matter it hosts? Or is it a rich and complex world unto itself, with rules we are only beginning to glimpse? Deep within the heart of an immense galaxy cluster, a cosmic rebellion is underway. The Phoenix Cluster is a titan, one of the most massive and luminous structures of its kind we have ever found. At its core lies a galaxy that should be dormant, a quiet giant lulled to sleep by the very engine that powers it. Instead, it is a stellar factory operating at a frantic, almost violent pace. This central galaxy is giving birth to new stars at a rate that defies belief, creating the equivalent of over 700 suns every single year. To put that in perspective, our own Milky Way galaxy might form 1 or 2 new stars in a year. The Phoenix Cluster is producing an entire stellar population in the time it takes ours to produce a handful. This frenzy of creation presents a direct challenge to one of the fundamental rules astronomers thought governed galaxy evolution, a process known as feedback. For years, the standard model was clear. At the center of every large galaxy, including this one, resides a supermassive black hole. As this black hole feeds, it becomes an active galactic nucleus, releasing unimaginable amounts of energy in the form of radiation and powerful jets. This energy was thought to heat the surrounding gas, preventing it from cooling, collapsing, and forming new stars. The black hole essentially acts as a cosmic regulator, shutting down its own galaxy's growth to prevent it from becoming too large. But the Phoenix Cluster is breaking all the rules. Here, in the most extreme environment imaginable, the black hole is not shutting down star formation. It seems to be losing the battle. Vast rivers of supercooled gas are flowing toward the galaxy's center, like a waterfall feeding a lake. Despite the intense heat from the black hole's activity, pockets of this gas are managing to cool rapidly and collapse, igniting into new stars at a rate that outstrips the black hole's ability to stop it. It is a breathtaking imbalance, a cosmic seesaw tipping wildly in favor of creation over destruction. This tells us that our understanding of feedback is incomplete. There must be a sweet spot, a delicate and temporary state where the black hole's fury is just enough to stir the pot of gas, but not so much that it boils everything away. In this precarious phase, the agitation might actually trigger the very collapse it is supposed to prevent. The Phoenix cluster offers us a rare glimpse of a universe in its most productive and chaotic youth, a place where the rules are not just being bent, but are being rewritten before our eyes. Dragonfly 44 is a ghost in the night sky, a galaxy that should not exist in its current form. From a distance, it appears as a faint, fuzzy smudge of light, so diffuse that it was overlooked for years, hidden among the thousands of galaxies in the nearby Coma cluster. But when astronomers finally focused their attention on this seemingly insignificant patch, they discovered a profound cosmic paradox. The amount of starlight coming from Dragonfly 44 is roughly equivalent to that of our own Milky Way, meaning it has a similar number of stars. Yet those stars are not concentrated in a brilliant disk. They are scattered across an immense, wispy cloud, making the galaxy incredibly difficult to see. The true nature of this phantom was revealed by studying the motion of its stars. They were orbiting the galaxy's center at astonishingly high speeds, moving so fast that, according to the laws of gravity, the galaxy should have long ago torn itself apart. The only thing holding it together is an immense, invisible source of gravity. When the calculations were complete, the result was staggering. While Dragonfly 44 has a stellar mass similar to the Milky Way, its total mass is thousands of times greater. This means that over 99.99% of this galaxy is not made of stars or gas, but of dark matter. It is a dark galaxy, a celestial body where the visible matter is little more than a sprinkling of dust on an invisible cosmic mountain. How does a galaxy form that is almost entirely dark matter? One theory suggests it was a normal galaxy that had its gas, the raw material for new stars, violently stripped away as it plunged through the dense environment of the Coma cluster. All that remains is its original massive dark matter halo and the old stars that were already formed, left to orbit in a ghostly memory of what once was. Another, more radical idea is that Dragonfly 44 was born this way. In the early universe, pockets of dark matter may have collapsed to form halos that, for some unknown reason, were incredibly inefficient at converting their gas into stars. They are failed galaxies, cosmic experiments where the normal process of star formation barely even started. The existence of such an extreme object forces us to ask fundamental questions about dark matter itself. If dark matter is truly cold and collisionless, as our standard models assume, why did it allow such a huge halo to form while gathering so few stars? Could there be a type of dark galaxy that has no stars at all? A perfect shadow in the void that our telescopes can never directly see. Dragonfly 44 is more than a cosmic curiosity. It is a laboratory for the invisible, a single, fuzzy patch of light that holds the key to understanding the universe's dominant, yet most elusive component. Another cosmic giant looms in the depths of space, a gathering of the universe's most brilliant beacons. Known as the Large Quasar Group U-1.27, this structure is not a wall of galaxies, but a colossal cluster of quasars, the intensely luminous cores of distant active galaxies. It stretches across an incomprehensible 4 billion light-years, a dimension so vast it once again pushes directly against the theoretical limits set by our understanding of the cosmos. Quasars themselves are not rare, but finding them grouped together in such a massive, coherent structure is profoundly unusual. These are not quiet neighbors. Each quasar is a ferocious engine powered by a supermassive black hole feeding at a tremendous rate, outshining entire galaxies. To find dozens of these cosmic lighthouses aligned across billions of light years suggests an underlying architecture of staggering proportions, a skeleton of the cosmic web built on a scale we thought was impossible. The cosmological principle, the idea that the universe should be smooth and uniform on the largest scales, implies a theoretical size limit for any single structure. That limit is calculated to be approximately 1.2 billion light-years. The large quasar group U-1.27 is more than 3 times larger than this. Its existence forces a critical question. Is this group a real, physically connected structure, or is it a chance alignment, a trick of perspective that makes separate objects appear linked? The statistical analysis suggests the odds of it being a random fluke are incredibly low. This points to a universe that is not just lumpy, but one that can organize its most energetic objects into patterns of a scale that our standard model of cosmology simply cannot accommodate. It hints that the seeds of cosmic structure, the initial density fluctuations from the Big Bang, might have been far more pronounced on larger scales than our models allow. Or perhaps it means that gravity has been working in ways we do not yet comprehend, weaving together threads of the cosmic web across distances that defy our current physics. This grouping of brilliant quasars is more than a collection of strange objects. It is a glaring anomaly in our map of the universe, a challenge written in the most intense light imaginable. The future of our galaxy is already written in the stars above us. A faint, sprawling river of suns and hydrogen gas is flowing between the Milky Way and the Andromeda Galaxy, a celestial bridge marking the first stage of an inevitable collision. Long before these two titans merge in a spectacular dance 4 billion years from now, their gravitational forces are already pulling at each other, stretching their outer halos into vast, luminous streams. These are not the neat, tidy spirals we see in textbooks. They are the frayed edges of galaxies, a preview of the chaos to come. The intricate patterns within these streams, however, are proving far more complex than our simulations predicted. When astronomers model this cosmic approach, they input the observed masses, speeds, and trajectories of both galaxies. Yet the real streams of stars show twists and substructures, kinks and overdensities that the smooth models fail to reproduce. This mismatch points directly to the invisible architecture of dark matter, the gravitational tug that is stripping these stars away and weaving them into streams depends entirely on the shape and distribution of the dark matter halos enveloping both galaxies. If our models of those halos were perfect, the simulated streams would look just like the ones we observe. The fact that they do not tells us that the dark matter halos of Andromeda and the Milky Way are likely lumpier, or perhaps shaped differently than we have assumed. The streams act like cosmic fishing lines, and the subtle wobbles in their flow are telling us about the hidden structure of the immense, invisible objects they are tangled with. This is more than a future cataclysm. It is a live experiment in galactic dynamics, offering a unique chance to map the dark matter that governs our local cosmic neighborhood. As we watch this silent exchange unfold, we are essentially reading the opening chapter of our galaxy's final story, written in the motion of stars pulled from their homes. This galactic drama is not confined to our future. A ghostly ribbon of gas already stretches across the southern sky, a testament to a gravitational tug-of-war that has been raging for billions of years. Known as the Magellanic Stream, this colossal structure is an enormous river of hydrogen, torn from our two largest satellite galaxies, the Large and Small Magellanic Clouds, as they dance around the Milky Way. The stream itself is breathtaking in scale, arching over the entire celestial sphere for more than 500,000 light years. For a long time, its origin seemed straightforward. The leading theory painted a simple picture of tidal forces, where the gravity of our Milky Way was slowly stripping gas away from the smaller clouds, much like the moon's pull raises tides on Earth's oceans. This should have been a clean, predictable process, but when astronomers tried to simulate it, their models failed. The simulated stream never matched the real one. It was never as long nor as massive, and it lacked the intricate filamentary structure we observe. The gas in the real stream is also curiously uniform. If it were torn out solely by the Milky Way's gravity, we would expect to see a clear chemical signature, a gradient from gas that came from the large Magellanic Cloud to gas from the small one. But the chemistry is mixed, suggesting a far more violent and interactive history between the two clouds themselves. The solution to this puzzle appears to lie in the invisible realm. Recent simulations now suggest that to create the stream we see, the Magellanic Clouds must themselves be shrouded in their own extensive dark matter halos. As these two clouds orbit each other, their dark matter halos would interact gravitationally, violently stirring their gaseous contents long before the Milky Way's gravity even became the dominant factor. This initial chaos would have ripped out vast amounts of gas, pre-processing it and flinging it into a long, massive lead that the Milky Way then further stretched into the majestic stream we see today. Without this dark matter component, the clouds would not have had enough gravitational leverage to create such a structure. The Magellanic Stream, therefore, is more than a beautiful cosmic scar. It is direct, observable evidence that even small galaxies are dominated by their own hidden halos of dark matter, and that the history of our cosmic neighborhood is written not just in stars, but in the intricate, invisible dance of the universe's most mysterious substance. Our own galaxy holds a secret shape at its heart. The Milky Way is not a simple, graceful spiral. It is a barred spiral with a thick, elongated structure of stars cutting directly through its galactic center. This bar is a colossal formation spanning thousands of light years, and it is not static. It rotates as a single, rigid unit, a slow and majestic turn that orchestrates the motion of hundreds of billions of stars, including our own sun. The existence of this central bar fundamentally changes how we understand our galactic home. It acts as a great gravitational engine, a cosmic traffic controller that herds stars and funnels immense amounts of gas inward toward the galactic core. This influx of material can trigger bursts of star formation and feed the supermassive black hole, Sagittarius A star, influencing the very activity at the galaxy's core. The bar's gravitational pull creates specific zones of stability, known as orbital resonances, which can either promote the formation of new spiral arms or disrupt them entirely. The Sun itself is thought to orbit in a resonance with the bar, meaning the rhythmic tug of this giant structure has likely shaped the entire history of our solar system. Yet for such a pivotal feature, its precise nature remains a subject of intense debate. Determining the bar's exact size, its rotation speed, and even its age is incredibly difficult because we are embedded within the galaxy we are trying to map. It is like trying to discern the shape of a forest while standing deep within its trees. Some measurements suggest the bar is relatively short and fast spinning, while others argue it is longer and rotates more slowly. Its age is equally mysterious. Did it form early in the Milky Way's history, or is it a more recent development, the result of a gravitational disturbance from a passing satellite galaxy. This is not just an academic question. The stability and longevity of the bar challenge our models of how spiral galaxies evolve. Simulations show that bars can form naturally from instabilities in a galactic disk, but they can also buckle, thicken, and even dissolve over time, potentially reforming in a cyclical pattern. The specific properties of our galaxy's bar tell us which evolutionary path the Milky Way is on. Is our bar young and dynamic, or is it an ancient, steady structure? The answer shapes our understanding of the galaxy's past and predicts its future, revealing that even the most familiar cosmic structures are still hiding fundamental secrets. Our galaxy's halo is far from a peaceful, empty expanse. Wrapped around the Milky Way's brilliant disk is the Virgo overdensity, a vast and tangled river of stars so close it spans dozens of times the width of the full moon in our night sky. This is not a distant structure, but a nearby stream, a ghostly remnant of a dwarf galaxy that our Milky Way is actively tearing apart and consuming. The stars within this overdensity are moving together on a long, looping orbit, a celestial parade that marks the final stages of a cosmic feast billions of years in the making. As our galaxy's immense gravity seized this smaller neighbor, it began to stretch it, pulling stars away from their original home and weaving them into this immense, diffuse stream that now envelops us. The sheer scale and complexity of this structure challenge the old, quiet picture of our galactic halo. We once imagined this outer region as a relatively settled and serene place, populated by ancient stars that had been in place since the galaxy's birth. The Virgo overdensity reveals a halo that is instead dynamic and violent, a place where the evidence of past collisions is still fresh and unfolding. This is not an isolated case. Astronomers are now discovering dozens of similar stellar streams crisscrossing the galactic halo, each one the torn-apart skeleton of a devoured galaxy or star cluster. Every stream tells a story of a separate merger, a unique chapter in the Milky Way's growth. We are coming to understand that our galaxy was not born in isolation, but built through a long and violent history of cannibalism, with smaller galaxies being shredded and absorbed to form the majestic spiral we see today. The quiet halo is in fact a cosmic battlefield, littered with the debris of countless collisions, a permanent record of the violent processes that shaped our home in the universe. But sometimes the most profound challenges come not from a single giant, but from a field of tiny, ancient specks of light. In 2003 and 2004, the Hubble Space Telescope performed a remarkable experiment. It pointed its lens at a seemingly empty patch of sky, a region so dark it was equivalent to looking through a soda straw, and it collected light for a total of 1 million seconds. The result was the Hubble Ultra Deep Field, an image that revealed thousands of galaxies, each one a faint smudge of light from the deepest reaches of time. These were not the grand spirals and ellipticals of the nearby universe. These were the first galaxies, infant structures seen as they were just 400 to 800 million years after the Big Bang. The sheer number of them was astonishing, but their nature was even more surprising. According to our best models of cosmic evolution, the universe's first galaxies should have been small, chaotic, and irregular, little more than scrappy clusters of stars struggling to coalesce from the primordial darkness. Yet many of the galaxies in the ultra-deep field appear more mature and structured than anyone expected. Some show clear signs of rotation, the beginnings of orderly disks. Others are already quite massive, having assembled a significant number of stars in a cosmically short period of time. This presents a fundamental timing problem. How could gravity have pulled together enough dark matter and gas to build these structured, massive galaxies in less than 1 billion years? It is like finding sophisticated, bustling cities in an era that, by all accounts, should only contain scattered, primitive villages. The existence of these precocious galaxies forces a dramatic rethink of the very first chapters of star and galaxy formation. Perhaps the first stars were born in incredibly efficient, explosive bursts, flooding their tiny galaxies with light far sooner than we thought. Or maybe the dark matter halos that served as the seeds for these galaxies were far more effective at gathering gas than our simulations predict. The Hubble Ultra Deep Field, a single image of profound emptiness that is in fact filled with 10,000 points of light, tells us that the dawn of the cosmos was not a slow, gradual awakening, but a sudden, brilliant sunrise. Far beyond the familiar orbits of Neptune and Pluto, the solar system does not simply end. It gives way to a vast and dark frontier known as the scattered disk, a region of icy bodies whose orbits have been stretched and twisted by gravitational encounters. And beyond even that lies the inner Oort cloud, a hypothesized shell of frozen worlds drifting in the deep freeze of interstellar space. Here, in this profound emptiness, we find some of the most peculiar objects in our cosmic backyard, like the dwarf planet nicknamed the Goblin. Discovered in 2015 and formally designated 2015-387, the Goblin is a small, icy world whose orbit is breathtakingly elongated. It takes 40,000 years to complete a single journey around the Sun, spending almost all of that time in the frozen darkness, only to make a brief, swift plunge into the slightly warmer inner reaches of the scattered disk. What makes the Goblin, and a handful of other similar objects, so extraordinary is not just their lonely, stretched-out paths, but the strange way these paths are aligned. These are detached objects, meaning their orbits are so far out that they are virtually disconnected from the gravitational influence of the giant planets. They should, in theory, be oriented randomly, pointing in all directions like a scattered handful of needles, but they are not. Instead, their orbits are clustered. They share similar angles of orientation, their elongated paths all pointing in roughly the same direction in space, as if they are all being herded by an unseen force. This peculiar clustering is the central clue in one of the greatest modern astronomical mysteries, the hunt for Planet 9. The hypothesis is as simple as it is revolutionary. A planet, perhaps 5 to 10 times the mass of Earth, lurking in the distant, dark reaches of our solar system, on an orbit that takes 10 to 20,000 years to complete. Its immense gravity, acting over millions of years, would be like a hidden shepherd, gravitationally nudging the orbits of these small, icy bodies into the strange alignment we observe. The Goblin and its kin are the tremors, the gravitational footprints of this unseen giant. This potential discovery challenges everything we thought we knew about our own cosmic neighborhood. Our canonical model of solar system formation never predicted a planet of this size and distance. Its existence would imply a dramatic, violent past, perhaps a gravitational ejection from the inner solar system that left it stranded in this vast, elliptical prison. The very structure of our solar system's outer limits, defined not by random chance, but by the orchestration of a hidden master, would force a complete rewrite of our solar system's history and architecture. We are left to wonder if we are truly alone in this cosmic house, or if a silent, frozen giant has been watching from the shadows all along. At the very heart of our galaxy, a silent, ghostly hourglass glows. This is the galactic center lobe, a colossal structure of polarized radio emission that stretches for hundreds of light years above and below the Milky Way's core. Unlike the brilliant stars we see in visible light, this lobe is invisible to our eyes, revealing itself only through the faint whispers of radio waves. It forms a near-perfect symmetrical shape, with two vast bubbles connected at a narrow waist, right where our supermassive black hole, Sagittarius' star, resides. This elegant structure is a direct window into the violent and complex engine room of our galaxy, but its true origin remains one of the most compelling local mysteries. What cosmic force could have blown such a perfect, immense form? The prime suspect is the central black hole itself. Astronomers theorize that in the relatively recent past, Sagittarius' star might have experienced a violent feeding frenzy, gorging on a nearby cloud of gas. This activity could have launched powerful, focused jets of energy and matter from its poles, inflating these giant radio bubbles like a cosmic glassblower, shaping a delicate ornament. The energy required is almost beyond comprehension, a testament to the raw power slumbering at our galactic center. Yet there is a competing theory. The region around the black hole is also a cauldron of intense star formation, home to dense clusters of massive, young stars. These stellar behemoths lie fast and die young, unleashing ferocious stellar winds and ending their lives in supernova explosions. A coordinated burst of this stellar violence could have created a different kind of outflow, a superheated wind powerful enough to carve out the lobe we see today. The debate continues because each scenario leaves a different fingerprint on the lobe's structure and the energy of its particles. A black hole jet would likely create sharper, more defined edges, while a starburst wind might produce a more turbulent and diffuse interior. Unraveling this mystery is like listening to the distant echo of a galactic explosion, trying to determine if the sound came from a single cannon or a volley of rifles. The galactic center lobe is more than a beautiful shape. It is a fossilized record of a recent cataclysm, a reminder that the quiet center we see today was not long ago a site of unimaginable ferocity. This final cosmic mystery is perhaps the most subtle, yet its implications are as vast as the universe itself. It does not involve a single, colossal wall or a brilliant quasar, but the silent, stately spin of billions of galaxies. Every galaxy rotates, a slow whirl of stars and gas tracing out a specific axis in space, a direction we would expect to be set by local, random forces during its formation. According to the cosmological principle, these axes should be oriented completely at random across the sky, like a countless collection of tops spun by different hands, pointing in every conceivable direction. Yet, some astronomical studies are finding something deeply unsettling. They suggest that the rotation axes of galaxies, separated by billions of light years, might not be random at all. Instead, they appear to show a faint but statistically significant correlation, a tendency to align with one another across unimaginable voids. It is as if an invisible, cosmic hand reached across the emptiness and gave them all a gentle, coordinated push in the same direction. This phenomenon, known as galaxy spin alignment, defies our most basic understanding of cosmic evolution. How could galaxies so far apart, which have never been in causal contact since the beginning of time, possibly know about each other's orientation? The gravitational influence from one to the other would take longer than the age of the universe to traverse the distance between them. This points towards a force or an influence that operated on a scale far grander than anything we have ever considered, something that imprinted a preferred direction onto the fabric of the cosmos in its very first moments. One profound possibility is that this alignment is a fossil, a frozen relic from the universe's birth. It could be the imprint of primordial gravitational waves, ripples in spacetime from the violent inflationary epoch that followed the Big Bang. These waves, washing through the infant cosmos, could have gently sculpted the angular momentum of the collapsing clouds of gas that would become galaxies, setting their spins in a coherent, large-scale pattern. Another, more radical idea is that we are seeing the influence of a cosmic magnetic field of unimaginable scale, a background field woven through the universe that exerts a tiny but consistent torque on spinning galaxies, slowly coaxing them into alignment over billions of years. If confirmed, this subtle correlation would be one of the most significant discoveries in modern cosmology. It would mean that the universe is not just lumpy in its distribution of matter, but also possesses a hidden texture, a preferred direction woven into its very fabric. The random chaos we assumed was fundamental would be revealed as an illusion, masking a deep and mysterious order that connects the spin of one island universe to another across the deepest abyss. This quiet alignment of galactic spins is a whisper from the dawn of time, a clue that the greatest organizing forces in the cosmos are those we have only just begun to sense. From the grandest walls to the faintest whisper of aligned galaxies, we have journeyed through a cosmos that defies simple explanation. Each of these 25 structures, from the Hercules-Corona Borealis Great Wall to the silent pull of the dark flow, represents more than a scientific curiosity. They are individual cracks in the foundation of our understanding, each one a direct challenge to the principles we once thought were unshakable. The universe is not the smooth, uniform place we once imagined, but a realm of staggering imbalances, hidden textures, and forces that operate on scales we are only beginning to perceive. These cosmic anomalies are not problems to be solved and filed away. They are guideposts pointing toward a deeper, more complex, and far more mysterious reality. They remind us that the map we have drawn is still incomplete, with vast territories marked only by the words "Here be dragons." The greatest discovery is not any single structure, but the collective realization that our fundamental models of physics and cosmology are being stretched to their breaking point. So we turn this final question to you. Which of these cosmic mysteries captures your imagination the most? Is it the perfect ring of galaxies, the ghostly pull of the dark flow, or the possibility of a hidden planet, 9, shaping our solar system from the shadows? Share your thoughts in the comments below, and subscribe to continue these journeys to the very edge of understanding.